Okay, our goals now are twofold. One is we're going to derive those potential energy of gravity and potential energy of spring functions. You've used them, mgh and 1/2 kx squared or s squared, whichever you use. I wouldn't use mgy, we'll see why in a minute. But we're going to look at them very carefully. And we're going to look at the derivations, and then we'll look at some more stuff that comes out of that. Because again, potential energy is very, very useful. We use it in quantum mechanics all the time. It's great. You need to have an understanding here and not just do the math. But you also need to learn how to set up the math and let the math kind of do the work for you. If you have some intuition for what that is, then that's great. So we're going to do both of those things. Set up the math and have a real deep understanding of what potential energy is. Okay, so behind the scenes is a force, really. Interactions cause change. Net force causes an acceleration, right? We said if we can mess with that, turn it into this equation, the net work, or total work, from all forces causes a change in kinetic energy. So this includes, acceleration includes changes in speed and direction. When we're dealing with energy, we're leaving out the changes in direction part. So that's an interesting thing to note. In other words, we said last time, if the force is perpendicular to the path, you're not doing any work. You can turn it, you're doing something. That's not what we mean by work. What we mean by work is speeding it up or slowing it down or changing the kinetic energy. Okay. Then we saw, when we derived form 2 in that video, that we could split the work into non-conservative forces and conservative forces, move the conservative forces over here, rename them, and call this the change in mechanical energy. That is, E later minus E earlier. Sorry about the capital E's, but I think it works out best. That's all of the kinetic energy, translational, moving, and rotational soon, plus all the potential energies. If you got a spring, if gravity is changing, gravity is not changing, don't put it in at the later moment. Minus all, hello, did it again, plus, got minus happy, plus all the potential energy at the earlier, sorry, better watch these. Okay, so what do? You look for energy accounting at all the energy earlier, then you look, what have you got later, and then you see if there's any interactions that cause the change in this energy in between the states. So here's going to be a key theme, it's that is happening between some earlier and later state. Work is not a state variable. I'll say it multiple times. It's not a big deal, but it is a big deal. It's not hard to understand, but it's a big deal, I should say. So mechanical energy, kinetic all plus potential energy all. We're going to turn our potential energy change. Really, the definition of potential energy is we define the change in potential energy. That's the definition. By definition, by moving it over. It is a force. There is an interaction by force. It's the work done by that force. And it is the negative, and we'll explore that, of the work done by the associated conservative force. That is, the change in potential energy of gravity is the negative work by gravity. Change in potential energy of the spring is the negative work by the ideal spring. Atomic, etc. Okay, cool. Notice that this, again, is not a state variable. That is, you don't have this at an instant. You don't have work at an instant. Okay? This is a change, so that's really not a state variable either. The cool invention, the whole reason for doing that is to turn this into state variables. Hey, how much potential energy do I have earlier? How much potential energy do I have later? That's so much easier to work with because I don't have to follow it from the earlier to later. I don't have to integrate it from earlier to later. So that's great. But we do have to set or define where 0 is. It's set, it's chosen. Okay. So that is a deep understanding. It's a little bit that goes a long ways. Recall that force can be written in component form, Fx, I hat, and so on. ds can be written in component form. And if it only moves radially, which we're not going to do right now, but then it's dr r hat. So these are very useful things. Right? So we're going to turn a path function into a state function. Don't worry too much about that. Let's take a look at it. Okay, let's do gravity first. Gravity. Potential energy due to the force of gravity, which if you let it, and then gravity is the only thing working on it, if it slows you down, it'll speed you up if it's the only one. So the change in potential energy, by definition, is the negative work due to the force of gravity. Okay. We took it from one side, the forces, the interaction side, over to the other. We need to write force, and we need to look at the path. So force of gravity is mg down. Call that plus, it doesn't matter. The force is down. If I call up positive, then what have I got here? Is that correct? Down is negative. If I call down positive, then I got positive mg j hat. But physically it's down. So let's work with it this way. Now I can work with it just as well that way, but we'll see why. So I have to be careful here. It's a negative this. If I'm going to use this definition, then down is negative j hat. And so I need to put, this is the tricky part, the negative. So I'm really getting that in there. All right, negative mg j hat dotted with ds is the miss. But you know about the dot product, the scalar product. Let's see. This dotted with this, that's 0. This dotted with this, that's 0. And so I got a negative and a negative because of my coordinate system. And I'm going to get that as, well, wait a minute. What have I got here? Let's put this in as a positive. This is the integral E, L, mg. What's j hat? Dotted with dy j hat. J hat dot j hat is 1, so dy. Oh, wait a minute. That's positive. Mg is a constant. Integral dy earlier to later. And so that finally gives me that, hey, that is mg y later minus mg y earlier is delta u. So this is the true definition. Notice the negative worked out nicely here. You should try it for the definition of positive being down. It's still, you know physically that if I raise this up, physically, no matter what your coordinate system is, this is getting more potential energy of gravity, more potential for kinetic energy. Right? That could be a 0 where you set 0 is up to you. All right? So it shouldn't matter, and the derivation should work, so that's an exercise for you. And what I've got here as a conclusion then is I can either say that delta U of gravity is equal to mg y, no, excuse me, my punchline over here. What I want to do here is emphasize that if I call y positive up, then going up increases y. If I call y positive down, that gets a little bit funny. I still get more potential energy up here. Now, for the sake of expedience here, I'm going to then just do this and say, the important thing to do is look at the change in height. You can play with that and work that out. That's a good puzzle. But independent of whether I call plus up or plus down, I'm increasing potential energy as I go up. So I really think that h, a lot of books will use y. H is a much better variable. Okay, and that allows me to say, oh, the potential energy gravity at any state is equal to mgh at that state. But that's not the definition, because you have to include, if you're going to turn it into a state variable, where u is set to 0 at wherever h is set to 0. So once you set that reference, you're good. Okay, cool. So let's see, as I move, for example, if I think about this intuitively, if I move along the path here, I'm going here, I go up, I go sideways, I go up, I go sideways, I go down, I go over, whoop, up and around on a curve. The beauty of this is it doesn't matter how I get from one height to another. That's another definition for conservative forces. You say it's path independent, and you can prove it mathematically in your course. If I start here, let's say that's h1, I don't know wherever I define it to be 0, and I go to h2. Well, let's see, force of gravity is this way. My path is this way. The force, the work due to that force, you can see is 0, perpendicular path. Now, as I go up here, and someone's lifting it, whatever, I'm not worrying about all the other forces. As far as gravity is concerned, you're moving up, and therefore gravity is trying to slow you down. Doesn't mean it can't speed up from some other force, but gravity is trying to slow you down. So there's a negative work done by gravity. If the work done by gravity is negative, the change in potential is positive. The work due to gravity is negative, change in potential is positive. The work due to gravity is negative, it's taking away kinetic energy, but it's storing it in the United Bank of Gravity. Not really, it's really the force, but it's a good bookkeeping thing. And it'll give it back if you drop and fall off. And then again, I go over here. And it doesn't matter how much I move sideways, because if I just go from here straight up to here, I still get mg delta h as my change in potential energy, independent of the coordinate system. Going sideways doesn't do anything. Going up does. Force of gravity down, moving up, gives a negative work from the force of gravity. But if you move it to the other side, a negative becomes a positive, and you're increasing the potential energy. Clearly, you're increasing the potential energy. Now you're going over sideways, fine, it doesn't matter, no work done by gravity. Now you're going downward there, but the force of gravity is also downward, so if you let it, force of gravity will speed you up. It's certainly trying to, doing positive work, and as the work is positive, the change in potential energy is negative, that is, you're losing potential energy, as it were. So they're really saying the same thing. It's just by moving the work over to that other side of the equation, we get to just look at before and after, and we don't care about the path. We don't, you know, if I go along here, whatever, if I start here and I end up here, all I know is that I went up that amount, delta H. And if I start here and I end up here, then that's my delta H. And that's the beauty of potential energy. That's why we invented it. That's what it is, but it's really a force, right, an interaction. Okay, cool, let's go over here real quick. How are we doing?
You're good, 10 minutes.
So, got that. This is really not the definition, mgh. It's got to be AMGH relative to an h, which is this, another way of saying it's got to be delta U that we're really defining. And it's the delta U which is really a work over the path. But the path doesn't matter. All that matters is how much you go up or down. That's why we can move to the other side and not worry about tracking it. Just where'd you start? Where'd you end? Okay, that's the essence of conservative force. Also works for a spring force or ideal spring force. Beautifully. There's various ways to get this. But the potential energy due to an ideal spring force, also called an elastic force, so the flexibility of materials also can be modeled this way very, very nicely. It's called, the ideal spring force is a linear force. If you double the stretch or compression, you double the force. Hooke's law. Right? stick some mass on some spring that has a certain strength. So that tells you how many newtons of strength, of force, you get per however much you stretch or compress. I'll set up a coordinate system, do this on a horizontal track. You can use S to talk about the stretch or compression. We generally take the equilibrium place to be 0. And so we've got a maximum, often called the amplitude, we'll get that out later, plus A, and then the minimum, negative A. We can call this the plus S hat direction. I'm going to do it in terms of X, so I'm going to call that the I hat direction, and I'm going to call this plus X, and we can use the X variable here. That's fine. So it doesn't matter, right? Don't memorize the symbols. So if that's true, then I notice that the force is negative K X I hat. That is, when X is 0, the force is 0. When X is positive, anywhere over here, the spring's pulling back in the negative direction. X is positive, force is negative, I hat direction. X is negative, and the force is negative, negative, or positive, that's right. So I could be moving this way and the force is back slowing me down. I could be moving this way, the force is in the direction of motion, speeding me up. So we'll talk that through in a moment. There's an equation for the force. Here's an equation for displacement in general, x, y, and z components. Here's the definition for potential energy change, in this case the spring. It is the negative work from that conservative force. It's the negative work from the conservative force between states, earlier and later. It's the negative work for that force, negative kx I hat, negative important. Put it in explicitly. Don't skip too many steps. Write that, then you can go plus. Dotted with the x, that whole mess right there, right? Wait, I hat dot I hat is 1. I hat dot j hat 0. I hat dot k hat is 0. So that and that are 0. So that leaves me with dx coming here. Right? I got a kx and a negative, negative. Now I go ahead and make that shift. What's the integral of kx dx? Well, it's 1/2 kx squared. Earlier to later. Now you could also do this if you don't have calculus by saying it's a negative work to the spring, which is the negative average force. And so we did that before, that the average force for a spring is 1/2 kx times x. So you could look that up again if you didn't have calculus. But we do, and we got this, and we say, okay, well that's 1/2 kx later squared minus 1/2 kx earlier squared, which we can turn now into a state function, potential energy later minus potential energy earlier of that spring. So it comes out really nicely, and you can understand in many, many different ways, and you can just work with it back in the old energy accounting ways, but you have a deeper sense of this. And again, we're going to look at those potential energy and energy versus position or x graphs, and look at stability as well. And just realize it goes really deep into quantum mechanics and so on. So what do we have? I mean, this will get you the answer. If x is 0, we're calling that equilibrium, so I've got no potential energy. The more I compress or stretch, it's still a positive number. And I can see that if I'm moving in, so let's kind of walk that through, be done with this. That's my 0 position. So suppose my velocity is this way. Well, what direction is the force? It's this way. So just looking at it intuitively, the force is opposite the motion, so the work is, in this case, the work due to the spring is negative, which is synonymous with saying the change of potential energy is positive. As you come in here, you're getting more and more potential energy. It's taking away kinetic energy is what that says. Or you can say it's storing energy. It's not stored anywhere, really. The United Bank of Ideal Springs. So it's a good way to bookkeep. We've moved this to the other side of the equation. Hence making the negative a positive. As it slows it down, we think of it as being stored. But you don't need both. Just use one. Potential energy is the nice way to do the energy accounting. So we don't need that. Now, let's do this. As it comes out, well, it's on this side of the equilibrium, so, oops, V. As it's moving out, clearly then, the work due to the spring is positive, and you're losing potential energy. It's less compressed. So again, look at it one way or the other. This is a nicer way, easier way to look at it. And then you do it as it continues over here. If the velocity is this way, well, on this side, the force is here. So what's happening in terms of work? Potential energy. Then it goes out there, and then it comes back. What's happening? Work, potential energy. Opposite signs. Think that through, just, by the third or fourth time. It all kind of makes sense. And then you can go ahead and crank that mathematical wheel, set it up correctly, and it matches intuition. And you're good. So I think those are nice derivations. In general, if you had a potential energy function, someone just kind of made up this force, conservative force, you could take that force and use this to derive the potential energy function for that force. We're going to see in the next video how if you had a potential energy function, you can differentiate it and find what that conservative force is, find the formula for that. So if you have the conservative force, you can get the potential energy function. If you have the potential energy function, you go backwards or differentiate with the negative to get the formula for the conservative force. And that's quite useful. We'll tie that to our graphs of energy versus position, and you'll have a nice deep sense, and we'll talk about stability. Equilibrium, stable equilibrium, neutral equilibrium, and unstable equilibrium. Okay, cool. That's for next time.